Okay, this is lesson 6.4. This is over rational exponents. And when we talk about rational exponents, okay, rational numbers are any numbers that could be written as a decimal or fraction. And what we're talking about by rational exponents is having fraction exponents. Okay, and this ties right into radicals. We can write an expression, okay, in exponential form or radical form, and they have the same value. It's kind of like going from fraction form to decimal form when you're just dealing with numbers, like 1/2 as a decimal is 0.5, but 0.5 is also equal to 1/2. We can go backwards and forwards, two different representations that mean the same thing. So today you're going to learn how to go from exponential form, an exponent with a base, and then to radical form and vice versa. And then we'll do operations with them. It's super, super fun. So we could be in exponential form. Let's start right here. If we have our base a, and it's in exponential form because it's raised to the 1 over n power, this is read as the nth root of a. And that n, notice it's in the denominator, and that represents the root. So we could say if we're in exponential form, that's a to the 1 over n power. And in radical form, okay, our base a becomes the radicand. It's to the first power, and we're taking the nth root. So remember, the root is always the index. Okay, root means index. It's the same thing. Now, what if our power is not 1? Okay, we could say a to the m over n power, which is really read as the nth root of a raised to the mth power. The math's really awesome that we get to make words like nth and mth, and they're like real words. It's pretty awesome. But that would be our base a, okay, to the m power. We keep m right here. And the nth root means we do a radical and we put that n value on the outside. And I try to explain it in class that there's always a rule, okay? M is the power, always, okay? The number on top is a power, and the number on the bottom is the root or the index. And I explained that powerful people like kings, queens, presidents, they always elevate themselves. They're above everybody else. And they even do it when they speak to you. They go up on high, and they're just, anyways, any people of power like to be elevated or on top of everybody else. And then we think of roots. Roots grow down. They don't grow up. Roots grow down. So the root is always the bottom number. And when we break these apart, you're going to see a little pattern too. We have to break up the fraction. One stays with our base inside and one goes outside the radical. And let me tell you, if I had a power, like I could fly, a superpower, I'd want to keep that power. So our variables always, or bases always keep the power with them, because who doesn't want to keep their power? And the roots always go on the outside. So on numbers 1 through 9, we are rewriting. Okay, we're going to write each expression it says in radical form. It has an exponent, that's a fraction. We're going to put it into radical form, and then we simplify that radical if needed, and simplifying is a part we've been doing for a long time. So here we have x to the 1/4 power. Again, 1 is the top number, that's our power, and we keep it. 4 is the root. Okay, so we say this would be x to the first power, and then we take the 4th root. And really, we don't even need the 1 as the first power. We would just say this is the 4th root of x. And that's done. Because if we only have one x inside, we can't pull any x's out. Because we'd have to have 4 in order to do that. Because of that 4th root. On number 2, okay, we have 15n as a grouping. And we're taking the 1/2 power. So we have 15n. And this right here, that's our power again. And it's to the first power, which means it stays the same. Now, 2 is our root. So we make a radical sign, and we could put a 2 there, but we don't even need it. Remember, if it doesn't have a number there, then it's an implied index of 2. So this is just a square root of 15n, and then I would think, can I break down 15? Nope, it's 3 times 5. There's no perfect squares that multiply to make 15, and we only have one n. So this is done. Okay, so whenever you see, okay, 1/2 power, that always means a square root. Always. And you notice here 1/4 power meant a 4th root. So we have a 1/3 power here. What could that mean? Okay, let's look. We have 24 to the 1/3 power. So I have 24. It's to the first power. It stays with it because it's its power. We keep our powers. And it's a root of 3. So we have the cube root of 24. And it would be so lovely if we were done But we're not done because I know that 24 can be simplified. There's a factor of 24 that's a perfect cube. Again, we have a cube root. So think of this, you're using your note card, the cube root of 8 times 3, because 8 is a perfect cube. The cube root of 8 will come out. The cube root of 8 is 2. So we have 2 on the outside, and we're left with a cube root of 3 on the inside. So this right here, 2 cube root 3 and 24 to the 1/3 power, okay, they're the same, but they are written in different ways. So again, 1/3 power, let's make that connection here. That means a cube root. Cool, let's keep going. All right, number 4. Okay, we have 7 to the 2/3 power. We need to write this in radical form. So my base is 7. Its power is 2. It keeps that. And our root is 3. That goes on the outside. Now notice 7 squared. That's like 2 numbers. We calculate it when we just have numbers. Okay, 7 squared is 49. So we say this is a cube root of 49. And then we check, does 49 simplify? Is there a perfect cube that divides into 49? The cubes that are smaller than 49 are 27. 27 does not go into 49. And 16. No, not 16, sorry, that's a perfect fourth. 8. That's what I meant. 8 does not go into 49 either. So this is done because none of our cubes divide evenly into 49. And then on number 5, we have k to the 7/2 power. All right, we can do the same thing with our variables, and we know how to simplify these once we get it into radical form. K is to the 7th power. It keeps its power. And then this right here is our root. Remember, root means the index. So it's a square root of k to the 7th. That means I have 7 k's underneath this radical, and I need to take some of these k's out because 7 is more than our index of 2. So if I kick out 1 k, that leaves me with 6. 6 and 1 do add back to 7. And we can square root k to the 6th, the biggest part of it. The square root of k to the 6th, remember we divide the exponent by 2. So k cubed, or 3 k's, come out, and we're left with the square root of k inside. And now it's done. Okay, number 6, we have 3 to the 5/4 power. So we say 3, my base is going to keep its power of 5 because it's always power over root. And we're going to take the 4th root of it. Now we need to say, what does 3 to the 5th equal underneath here? So we have the 4th root. 3 to the 5th power is 243. Because we're dealing with 4th roots, okay, look at 4th root, we're going to look at our fourths list. Which of our fourths go into 243? And it would be 81. So we would think of 243 as being the same thing as 81 times 3. And because 81 is a perfect fourth, we root that part of it. Okay, we bring out 3. That's the 4th root of 81. We're left with the remainder of the 4th root of 3. And that's our final answer. All right, continuing on. We have on number 7, AB, both of them, because we have those parentheses around it, being raised to the 3/4 power. Okay, so right now we're keeping A and B together. We're going to say A and B. Okay, remember writing in radical form means we keep our power, which is the top number 3. We put our radical sign, and the index is 4. That's our root. Root and index mean the same thing. Now, if I wrote it like this, A, B, and then cubed it, only the B is getting the exponent of 3. So that doesn't mean the same thing as what we need to do on this problem. They're both being cubed, so that means the cubed goes to A and to B. So this would be the 4th root of A cubed and B cubed. And then I would check to see if I can pull any A's or B's out. To come out, we have to have groupings of 4, because we divide by 4 to let out of a 4th root house. And we only have 3 of each, so our exponent is smaller than our index, so we are finished. Okay, number 8. Okay, we have negative 6x. Both of them are being raised to the 2nd power, and then we're going to cube root it. So you can kind of take shortcuts. Know that the bottom number is a root, goes on the outside. And then I have negative 6 in parentheses squared. That's a positive 36, because it means negative 6 times negative 6. 2 negatives make a positive. And then x is also squared. And then because it's a cube root, we're looking at our cubes list. Okay, 36 perfect cubes. We have 1, 8, then 27. Does 36 divide by 27? Nope. Doesn't divide by 8 either. And we only have 2 x's, so we have to divide by 3 to let them out. So there's no simplifying we can do. This is the final answer in radical form. And then last for this section, we have 7 times 12w to the 1/2 power. Now this 1/2 power is only being applied to what's it's touching, the parentheses. So 7 is going to stay on the outside. And again, 1/2 power right here means a square root, and 12w goes inside of it. Now 12w, we can break that down a little bit. 12, we know there's a perfect square that goes into 12. So we have 7 on the outside, and I would think of 12 as being 4 times 3, and I'm going to leave the w with the 3 because there's only one w. We can't let any w's out. It's not bigger than our index. So we take the square root of 4, which is 2. It multiplies with the 7 that's already out there to make 14, and we leave the square root of 3w inside. We couldn't use that factor as a perfect square. Okay, for this next section, we're going to do the opposite. We're starting in radical form, and again, you should notice it's radical form because they all have radicals on them. Crazy! And we're putting it into exponential form. Okay, so remember, we start, our radicand is the base. So 16 is our base, and the base is what gets raised to a power or an exponent. So what is 16's power? Because it always goes power over root. 16's power is 1. It doesn't have an exponent, so it's 1. Its root is 3. So we say this is 16 to the 1/3 power. And once we write these in exponential form, we're done. So this is like our favorite section of the notes because it's the easiest. On number 2, we have the square root of x and y. So we have to think about the correct way to write this. Sorry. Okay, I cannot just say xy to the 1/2 because only the 1/2 would be touching like only the y, and that's not the same thing. X wouldn't be under the radical if we wrote it that way. So if you have more than one variable or a coefficient and a variable, a number and a letter, you have to group them in parentheses and then do your power over root. So we're going to say xy as a grouping. There's one grouping of xy, so power of 1. And if there's not an index here, remember it's an implied 2, so it's a 1/2 power. And that's how it would be written. On 12, we have the 4th root of AW. So what is that in exponential form? We would put 8 and W together with parentheses, group it. It's a power of 1, and its root is 4. So it's 8W to the 1/4 power. Done. Hey, 13. Okay, we have the cube root of 11 squared. Again, your radicand is your base, so 11. Its power is 2, so that's powers are on top. The root is 3, so it's 11 to the 2/3 power. And now it's done. 14, we have the 4th root of k to the 5th. There's only one variable, so we're going to have k. Its power of 5 is the top. Its root is 4, so this would be written as k to the 5/4 power. Now in 15 and 16, we're going to shift things up a little bit. Okay, we've got the square root of 3m in the parentheses right here, and then all of that's being raised to the 7th power. So we've got two different powers happening here. Now 3m, okay, we work from inside the parentheses and work our ways out. So 3m, square root of 3m is inside of there. 3 and m need to be grouped together in their own parentheses. Its power, okay, because of the square root, is 1/2. Remember, 1/2 power is the same thing as a square root. And then all of that, we'll get parentheses, and we're going to put the 7. Okay, we're going to bring that down. Now this is our power rule. When you have a power, which is like 1/2 is a power and 7 is a power raised to a power, we multiply those exponents. So we'd say this is 3m to the 1/2 times 7 power, which just makes 7/2. So this is 3m as a grouping to the 7/2 power. And that's power rule. Power to a power means multiply your exponents. Okay, on 16, we're pretty much doing the same thing here as we did on 15. We have a grouping inside the parentheses we have to take care of first. We have negative 2a, okay, and its power is 1, its root is 4, so it's to the 1/4 power. But we have to wrap that up and bring down the 5th power that was outside of it. So this is our power rule. We multiply 1/4 and 5. Okay, that makes 5/4. So this would be negative 2a to the 5/4 power. And now it's in exponential form and it's done. Now 17 and 18, we could overcomplicate this if we want to, but notice we have a grouping, okay? All of 10 to the 5th power, a cubed, and b are all underneath a square root sign, which is a 1/2 power. So we're going to group that whole radicand together. So we have 10 to the 5th, a cubed, b, as one grouping, and we have one of those groupings, so 1 power, and the root is 2. So all of this is just to the 1/2 power. Again, that's synonymous with a square root. So it all checks out. Same thing for number 18. It's a cube root of everything that's underneath this radical. So we have our 9, x to the 7th, y to the 4th. Okay, we have one of those groupings, that's its power, and its root is 3. So it's raised to the 1/3 power. And again, that also means cube root, so it's done. Okay, now on the back side of our notes, we're going to do operations with our rational exponents. It's super fun. Okay, and the reason why we've learned all of this, so far we've just converted from one form to the other, but we learned a rule. When we multiply with radicals, they had to have matching indexes. Same thing when we divided with radicals, matching indexes or roots. And you know, like, that's really cool if every problem always had the same index, but they don't always. So we have this thing where if they don't have matching indexes, we can put them into exponential form, and then we use our exponent rules to simplify the expression. And once we get it down to one base and one exponent, we change it back to radical form and we simplify it, which is what we did on numbers 1 through 9. Okay, so we just do some operations with our bases first. So don't overstress. It's not a difficult concept. We've done a lot with exponent rules in Algebra 1, pre-algebra, and it does show up from time to time in Algebra 2. So on number 19, what we have here is x to the 1/3 power times x to the 4/3 power. We have a common base of x. Remember, the base doesn't change if it's common. But the rule is, okay, this is product rule, because we're multiplying, we add our exponents. This would be 1/3 plus 4/3. Now, what is 1/3 plus 4/3? It is 5/3. So see, I've got it down to one base and one exponent, and now we do what we did on numbers 1 through 9. We change it to radical form. So my base x is raised to the 5th power, that's the top number, power over root. 3 is the root, it goes on the outside. And then we see if we can simplify this anymore. Because I have 5 x's inside, we can split this up. So we make our 2 cube root houses. 5 does not divide by 3, and neither does 4, but 3 does. So we put 3 in the first, and we take 2 off. And again, 3 and 2 make 5. And we cube root our first house. That means we divide our exponent by 3, and that lets out 1x. And our remainder is the cube root of x squared. And that's our simplified radical answer. Pretty awesome. Now, number 20, okay, like this example, we have p to the 1/4 times p to the 3/2. Now, why, again, do we have to do it this way? Just to kind of show, this is what I showed in class. P to the 1/4 would be the 4th root of p. And p to the 3/2 power would be p cubed, and we're square rooting that. Now, we can't multiply these in this form because their indexes don't match. We have a 4th root and a square root. We cannot put p and p cubed together. Okay, so we would just be stopped. Couldn't do anything. But because we're in exponential form, we can use our product rule, which means we can add our exponents together, which allows us to simplify this problem in a way we couldn't have. So we keep our base of p, and we're going to do 1/4 plus 3/2. Okay, again, when you multiply, you add exponents. And this makes p to the 7th force power. Now that it has one base, we put it into radical form. So p keeps its power of 7, and we 4th root it. Because our power is greater than our index, we can pull some p's out of here. Okay, we think of this as 2 4th root houses. And 7 does not divide by 4. Then we have to kick out 3 to get to 4, which does divide by 4. And again, 4 and 3 make 7. So we didn't change value, we just rearranged it. We take the 4th root of p to the 4th, which means divide that exponent by 4. So only one p comes out, and we're left over with the 4th root of p cubed. Now it's fully simplified. Cute. Okay, number 21, a different exponent rule will be applied here. We have m to the 5/2 power divided by m to the 7th force power. Again, we have these matching bases of m, but when you are dividing with the common base, you subtract your exponents, and it is the top exponent minus the bottom exponent. So we have 5/2 minus 7 fourths. And if you don't like doing fractions in your head, it's okay, use your calculator. This would be our base of m to the 3/4 power now. And because we are to the 3/4 power, okay, we're going to write it in radical terms. Our m keeps its power of 3. The denominator is the root or the index. And because 3 is smaller than 4, we can't pull any m's out. This is done. Okay, that was using our quotient rule. Number 22, we have a to the 1/3 power being raised to the 5/2 power. This is that power rule again. When we have this power, like 1/3, raised to another power, like 5/2, we multiply our exponents. So I think of this as a 1/3 times 5/2, which would be a to the 5/6 powers. And again, do not leave it like this. We were asked to write it in simplified radical form. So a keeps its power, which is 5, the top number. Remember that whole thing, powerful people are on top. Roots grow down, so roots are on the bottom. So it's the 6th root of a to the 5th power. And because 5 is smaller than 6, this cannot simplify anymore. Okay, number 23, we have 32 to the 1/2 power being raised to the 1/2 power. So it doesn't change. 32 is still my base. So I'm going to take 32. It's to the 1/2 power, and we multiply it to the other power it's being raised to. We simplify those exponents first. And 1/2 times 1/2 is 1/4. So this is 32 to the 1/4 power. And now I put it into radical form. 32's power is 1, and then we take the 4th root. So if you look at your perfect fourths list, okay, my perfect fourth that goes into 32 is 16. 16 times 2 makes 32. So we write this as the 4th root of 16 times 2. And the 4th root of 16 is 2. So the 2 comes out, and we're left with a 4th root of 2 as my leftover piece. And now we have simplified that problem. Now number 8. Okay, we still got our power rule. We've got 8x squared, and its power it's being raised to, again, is the top number squared. So 8 squared is 64. Just showing it a little differently. And then x squared would be x to the 4th. And then the bottom number is the root. So we're going to cube root all of this. Now 64 is a perfect cube. Okay, and we have 4 x's, so we can take some x's out. So I would think of this as the cube root as 64. Let's keep 3 x's together. That meant we kicked out 1. So I just show it getting separated somehow. And then we take the root of our first term. The cube root of 64 is 4. We divide 3 by 3 to get 1 x that comes out. And we're left with the remainder of the cube root of 1x inside. Okay, now the next few examples have negative exponents as our rule. Now, contrary to popular belief, negative exponents do not make imaginary numbers, and negative exponents do not even make your answer negative. Okay, so I made everybody in class write this on their notes. Okay, let's see. We have, I'm going to scoot this over to the side a little bit. Okay, negative exponents. Okay, what do they do? It means just to take the reciprocal. And reciprocal means to flip, okay, your number or fraction. Take the reciprocal of the base. And then the negative sign leaves. It goes away. So maybe make a note of that, okay? The negative exponent just means to take the reciprocal of the base. The base is what's being raised to the power. Okay, and then the negative will go away after that, and then you can just do all the normal steps. Now, here's a crazy thing. We have 1/2 to the 100 to the negative 1/2 power. Someone might tell me that 100, we can't take the reciprocal because it's not a fraction. Remember, every number can be considered a fraction. Okay, if it's a whole number, we just put it over 1. So the first thing we're going to do is take the reciprocal, which means flip-flop these two things. It would be 1 over 100. And now we're going to put parentheses around it to the positive 1/2 power. The negative went away once we took the reciprocal. Now what is the 1/2 power? That means the square root of our base, which was 1 over 100 now. Now what's the square root of 1? Okay, that comes out as a 1. The square root of 100 comes out as 10. So the answer is just 1/10. Now, again, the square root of 100 is 10, and the reciprocal of that would also be 1/10. So it all kind of goes together. Now in 26, we have two different bases, and one does have a negative exponent. I would not take the reciprocal first. So I would say do whatever normal operations need to be done to simplify your expression down to one base and one exponent. Once it only has one base and you still have a negative exponent, then you would take the reciprocal. But right now I would apply my product rule first for number 26. I have 16, which is my base, to the 2/3 power times 16 to the negative 1/3 power. My base, I don't even multiply 16 and 16. That's my base. It doesn't change. We combine our exponents by adding them. Okay, so we have 2/3 plus negative 1/3 just means 2/3 minus 1/3. And that's 16 to the positive 1/3 power. So I did use that negative, but it just subtracted from 2/3, and now it's a positive exponent. There's nothing to reciprocal because there's not a negative left in the exponent. But I do need to simplify this. 16 to the first power, and then we're taking the cube root of that. We know that 8 is a perfect cube. So this is the cube root. We think of 16 as being 8 times 2, and the cube root of 8 comes out as a 2. We're left with a cube root of 2 inside. And now it's fully simplified. That's our equivalent answer. So on number 27, we have negative 216. It's raised to the negative 1/3 power. Now notice, I only have one base. It's negative 216. I don't have anything else to put it together with. So I'm going to reciprocal to get rid of my negative first. So think of this as negative 216 over 1. To get rid of the negative exponent, I'm going to flip it. So you have negative 1 over 216. And this is being raised to the positive 1/3 power now, which means cube root. We have the cube root of negative 216. And remember, we can cube root negatives because 3 negatives multiply to a negative number. So the cube root of negative 1 is negative 1. The cube root of 216 is 6. So this is just an answer of negative 1/6. Okay, 28. We have 112 over 7 to the negative 1/4 power. Again, I have one grouping here, so I'm going to get rid of the negative exponent first by flipping or taking the reciprocal of my base. So I'm going to say this is 7 over 112 to the 1/4. That's positive now. Now, whenever you're given a fraction, check to see if it reduces. Okay, 7 over 112 reduces to be 1 over 16. And that's what's really being raised to 1/4 power, and that will make it easier for us to simplify that radical. So again, 1/4 power means a 4th root of 1 over 16. And these are both perfect fourths. Okay, this 4th root of 1 is 1. The 4th root of 16 is 2. So this just simplified to 1/2. Very cute. Okay, numbers 29 through 32. I know you'll have questions like this on your test as well. These are some good ones. And this is really the whole reason why we're doing everything we're doing. Okay, I have the cube root of v times the square root of v. Okay, I can't do this problem the way it's set up because we have a cube root as an index and a square root. They don't match, so we can't do the problem in the form it's in. So we have to put it into exponential form and then do our exponent rules. So this v, its power is 1, its root is 3, so it's v to the 1/3 power, times, okay, we have a v, its power is 1, its root is 2, so it's v to the 1/2. I can apply my product rule, which means keep my common base, but add my exponent. So 1/3 plus 1/2 is 5/6, so this is v to the 5/6 power. And again, we're not done. We need to put it back to radical form now. So what this makes is v to the 5th power, and we'll take the 6th root. And I would check to see if this simplifies. I have 5 v's inside. I can't divide those by 6, so this is finished. Okay, it'll be similar for number 30. On 30, we have the 4th root of r cubed times the square root of r. Again, our indexes don't match, so we change it to exponential form. This r's power is 3, so that's on top. Its root is 4. So r to the 3/4 power times, Okay, the square root of r is a power of 1, a root of 2. So we're going to add our exponents because that's our product rule. So this is r to the 3/4 plus 1/2 power, which makes r to the 5/4 power. Okay, now we change it to radical form. So we say r to the 5th power, and we 4th root it. And then we think, can we take any r's out? We can, because 5 is bigger than 4. So we're going to break this up. We have our 4th root. We say we can divide 4 by 4. That leaves a leftover of 1. And the 4th root of r to the 4th that comes out is just 1r comes out, 4 divided by 4, leaving us with the 4th root of 1r still inside. Okay, now moving on, these are the last two examples. Okay, and this is where people get tripped up. I don't feel like enough time is spent on these types of problems in algebra because we see some voodoo math happen after a while. Okay, we have numerical bases, numbers. Okay, do not forget, you don't change your base. The base stays the same, and you apply your exponent rules, which is like add your exponents, subtract them, and so forth. So I have 4 over the cube root of 4. Well, I have common bases here. The common base is 4. So I would say this 4 in the top is to the 1st power. Just give 1 as a little placeholder there. It's over. Okay, we have 4 is my base, its power is 1, and its root is 3. Now, I always see some voodoo math. I see kids want to do 4 divided by 4 is 1, and we have 1 over 1, and 1 to the 1/3, and this is just 1, which is all incorrect. That's voodoo. Voodoo. Don't do that. So let's back up. If I have 4 to the 1st power over 4 to the 1/3 power, my base is 4. This is just like your quotient rule. We take our top exponent, we subtract our bottom exponent, but the base stayed the same, making this 4 to the 2/3 power now. 1 minus 1/3 is 2/3. Now we would convert this to radical form. Now 4 squared, okay, that's its power, is actually just a number 16. And then when we cube root it. And remember, 8 is a perfect cube, and it divides into 16. So this is the cube root we think of 8 times 2. And the cube root of 8 comes out as a 2. Our leftover is the cube root of 2. And that was the correct way to simplify all of that. Do not divide your bases. That's an illegal or voodoo math move. So on 32, my bases are 7. We're not changing those right now. My numerator, my base is 7, its power is 3, and its root is 2 because it's a square root. Over, my base is 7, my power is 1, my root is 2. Because these bases match, we can use our exponents rules, which is our base of 7, we have to subtract our exponents. 3/2 minus 1/2 makes 2/2, which is just 1. And what is 7 to the 1st power? It's just 7. And it's done. Okay. Good luck on your assignment. Keep track of your rules, keep track of which section you're in, and have fun.